Good morning, students. Today we will solve some numerical problems related to the chapter Magnetic Effect of Current, Electricity and Magnetism. So let us see the first question. 2 ampere current is flowing through a long straight wire. An electron is moving with a velocity 3 × 10 raised to 5 meter per second opposite to the direction of current, being at a distance 0.1 meter from the wire and parallel to it. What force will be applied on the electron by the magnetic field created by the current? Charge of electron is 1.6 × 10 raised to -19 coulomb. So, let us see the situation. A 1 ampere current is flowing through a straight wire. So, let this be the current I, which is equal to 2 ampere. An electron is moving with a velocity 3 × 10 raised to 5 meter per second opposite to the direction of current at a distance 0.1 meter from the wire. So, let me consider a point here where the electron is there and it is moving opposite to the direction of current with the velocity 3 × 10 raised to 5 meter per second and at a distance of 0.1 meter. So, this distance is 0.1 meter. So, this is what is given and then parallel to it. So, velocity is in this direction. What force will be applied on the electron by the magnetic field created by the current? So, we know that a charge moving in a magnetic field will experience a force given by F is equal to QVB sin theta. Q, charge of the electron, it's given. V, velocity of the electron, it is given. B is the magnetic field produced at this point by the current. So, we have to find B. How will we find B? The magnetic field due to a current carrying conductor at a distance A from it is given by, we have already learned the formula, mu naught I by 2 pi A. So, this is equal to mu naught. You know the value. What is that? 4 pi into 10 raised to -7. And current I, it's given as 2 divided by 2 pi into A. A is this distance, 0.1. So, when you calculate, you will get the value of magnetic field in Tesla. So, you can do the calculation by yourself and find the value of magnetic field. Now, what we have is theta. So, we have found B and then now what will be theta? The angle between the velocity of the electron and the magnetic field. We know that the direction of magnetic field produced by a current carrying conductor can be found using our right hand rule. What is the right hand rule? You have to hold your right hand, point the thumb in the direction of current, your fingers will curl in the direction of the magnetic field. So, if the electron is below this current carrying wire, the magnetic field will be inwards. So, here the magnetic field is inward. So, in this direction. Okay. Now, they didn't give the position of the electron, whether it is below the current carrying current or above the current carrying current. If it was above, then the magnetic field is coming out of this screen, right? So, it will be in this direction. So, either way, you know that if I just hold my two fingers in perpendicular directions, if I hold the first finger in the direction of the magnetic field, see, velocity of the electron is in this direction. So, the magnetic field and the electron's velocity are perpendicular to each other. Even in this direction, if I hold my first finger in the direction of field, the velocity of the electron is in this direction. So what is the angle between them? 90 degrees. And even if the electron was in front of the current at this position, again the magnetic field, if I hold like this, it is coming down, but the electron is moving opposite to the current, parallel to it. So downward and this direction, again 90 degrees. So wherever be the electron, the magnetic field makes an angle of 90 degree with its velocity. So here we can put theta is equal to 90 degree. Therefore, sin theta is equal to sin 90 is 1. So we got all the values. So we can directly substitute and find the value of force. So F is equal to Q, it is given 1.6 into 10 raised to minus 19 coulomb. Velocity is given, that is 3 into 10 raised to 5 meter per second into B, whatever value you get here, and sin theta is 1. So when you substitute all those values, you will get the value of force. So they have got the value of magnetic field as 4 into 10 raised to minus 6. 4 into 10 raised to minus 6 Tesla, and the force they have got it as 1.92 into 10 raised to minus 90. You are free to use the calculator, so do the calculation by yourself. Now let's see the next question. An object with charge 0.2 microcoulomb is moving with velocity 2 into 10 raised to 6 meter per second in a magnetic field along x-axis. If the magnetic field B is equal to 0.20 J cap plus 0.40 K cap Tesla, then what is the magnetic force acting on the charge? So the question is, what is the magnetic force acting on a charge moving in a magnetic field? So we know the equation to find the force on a charge moving in a magnetic field in the vector form, because magnetic field is given in the vector form. So let me use the vector form of the equation. F is equal to Q into V cross B. Now we have to express both the velocity and magnetic field as vectors and find their cross product. Do you remember how to find the cross product of two vectors? If you don't, let's see now. So velocity V is equal to 2 into 10 raised to 6 meter per second in a magnetic field along the x-axis. So we can express V is equal to, along x-axis, what is the unit vector? I. So V is equal to 2 into 10 raised to 6 I cap. Okay. Now we know what is B. B is equal to 0.20 J cap plus 0.40 K cap. Let me verify the velocity is 10 raised to minus 10 raised to 6. Okay, meter per second. Okay, this is the way it can be represented. Now remember, when you have two vectors in the form, vector A is equal to AXI plus AYJ plus AZK, and another vector B is equal to BXI plus BYJ plus BZK. Then how will you find A cross B? You will have to take a determinant, and in the first row you have to give I, J, K, and the second row the coefficients of A, which is AX, AY, AZ, and in the third row you will have to represent BX, BY, BZ. And the determinant, you already know how to find the determinant. That is I times, you have to multiply these two. Neglect this column and this row. So you have AY, BZ minus AZ, BY. You have to cross multiply these two, but you have to put a minus sign in between. This is just to remind you how to take the cross product of two vectors, which you have already learned in physics, and also now you must have learned that in math. So AZ, BY and minus J cap. Alternate terms, you have to change the sign. So minus J cap into, you have to multiply this and this, minus this and this. That is AX, BZ minus AZ, BX. AX, BZ minus AZ, BX. Then the next term will be plus K cap into, you have to multiply these two, AX, BY minus AY, BX. So my K cap into AX, BY minus AY, BX. So this is the method of finding the cross product of two vectors. Here we will use this method in order to find the cross product of these two. In those directions where there is no velocity or magnetic field, you can put it as 0. So let me represent V cross B is equal to determinant I, J, K. You have along I, that is x-axis, 2 into 10 raised to 6 velocity. And then J direction and K direction, there is no value. So I'll put here 0, 0. Now B is in J and K direction. In I direction, there is nothing. So I'll put here 0. And in this direction, I have 0.20 and here 0.40. So now let us find the determinant. Determinant is equal to I cap times 0 into this. What will be the value? 0. Minus 0 times this. What will be the value? 0. 0 times something is 0. Minus J cap. Now you have to neglect this column and this row. So 2 into 10 raised to 6 times 0.40. You have neglected this column. So these two minus these two. So 2 into 10 raised to 6 multiplied by 0.40 minus this times this. 0 into 0, which is 0, plus K cap into, you have to neglect this and this. So 2 into 10 raised to 6 times 0.20. So 2 into 10 raised to 6 times 0.20 minus 0 times 0, which is 0. So you got the value. This is equal to, along I direction nothing is there. 0 minus 0 is 0. So 0I. Then you have minus J cap into this times this. So you will get it as 0.80 into 10 raised to 6. 2 times this value. Now plus K cap times, you have 2 into 0.20, which is 0.40 times 10 raised to 6. So 10 raised to 6 is common, so I can take it out. So I can write finally force F is equal to, don't forget charge Q. What is the charge given? 0.2 microcoulomb. So instead of Q, I am substituting 0.2 microcoulomb. Micro means 10 raised to minus 6. So 0.2 times 10 raised to minus 6 times this. This is V cross P. We got V cross P. So to charge, I have to multiply V cross B. So V cross B is this quantity. I am multiplying that here. So times, there is no space here. So I will write here minus J cap into 0.80. And 10 raised to minus 6, I am going to take outside. So I am writing here 10 raised to 6. Then plus, with K cap, what do I have? K cap into 0.40. This is equal to, here 10 raised to minus 6 times 10 raised to 6. 10 raised to minus 6 plus 6. So 10 raised to 0, which is 1. So these two will get cancelled each other, or 10 raised to minus 6 is 1 by 10 raised to 6. So they gets cancelled each other. So what is remaining? 0.2. So 0.2 into 0.80. So we have to multiply 2 times 8. What is it? 60. So, or you can directly use the calculator, no issues. So minus, you will get 0.16 J cap plus 0.2 times 0.40. So it will be 0.08 times K cap. Let me verify whether this is the answer. Yeah, this is the answer. And what is the unit? Unit is N, Newton for force. So I hope this is clear to you. If it is not, just rewind a little bit and watch this again in order to clarify how the vectors are multiplied, how we take the cross product of two vectors. Revise that if you are not clear. Now, let us see the third question. A wire of mass 5 into 10 raised to minus 3 kilogram, 0.6 meter long and of resistance 0.1 ohm is kept perpendicular in a magnetic field of 1.8 into 10 raised to minus 3 Tesla. 4.5 volt potential difference is applied across the two ends of the wire. And they have given magnetic intensity H is equal to 1.8 into 10 raised to minus 5 ampere per meter. So they have given this figure where a magnetic field is directed into this plane and there is a conductor carrying current I. How much is the magnetic permeability? So A part of the question, how much is the magnetic permeability? We have learned equation, magnetic intensity H is equal to B by mu, right? Magnetic field divided by magnetic permeability. So inside the material, the magnetic permeability mu will be equal to B by H. I have taken mu to the side and H down. So B is given. What is that? 1.8 times 10 raised to minus 3 divided by H is also given. 1.8 into 10 raised to minus 5. So you will get as equal to 10 raised to 2. So this is the value of permeability. So you got the value of permeability and now we have to find, okay, let me read this question B. The wire will remain in equilibrium in the magnetic field B. Justify. So we know that a quantity or some object will remain in equilibrium if the net force acting on it is 0. If it is not moving, which means the total force acting on the body will be 0. Let us first find what are the forces acting on this conductor. There are two forces acting on this conductor. One is the gravitational force that acts on every body. So you have gravitational force acting downwards. How will you find the gravitational force? Fg. Let me express gravitational force as Fg is equal to mass into acceleration due to gravity. Okay? And we know that the current carrying conductor is placed in a magnetic field. So there will be a force, magnetic force acting on the current carrying conductor. How can we find the direction of that force? You have to take your left hand. So take your left hand, point the first finger in the direction of the magnetic field, that is into this board. The second finger in the direction of current, okay, and the thumb will give you the direction of force. So magnetic field, current, thumb is pointing upwards. So the force due to this magnetic field will be upwards, Fm. So let us find Fg, which is acting downwards, and let us find Fm, that is the force due to the magnetic field, which is directed upwards. If we find that both of them have equal magnitude, they are in opposite direction, so the net force becomes 0 and they will stay in equilibrium. So let us justify mathematically by finding the gravitational force and the force due to the magnetic field. So B part. How will you find Fg? Fg is equal to m into g. M is mass. Mass of the wire is given. Is equal to 5 into 10 raised to 3 kilogram. And g is acceleration due to gravity, which is a constant. We know the value, it's 9.8. So you can calculate this value, and then we have to find the force due to the magnetic field. What is the force acting on a current carrying conductor placed in a magnetic field? F is equal to ILB sin theta. So ILB sin theta. What is I? Current through that. Is it given? No, current is not given. But they have given resistance and potential. So we can find I, right? Let me use this space to find I. I is equal to voltage by resistance according to Ohm's law. So voltage is given, what is that? 4.5 divided by resistance is 0.1. Divided by 0.1 means multiplied by, this is 0.1 is 10 raised to minus 1. So when it go to, so this will be 45. Oh, that's a large value, ampere. So, or you can directly substitute that. So we can have here, instead of I am putting 4.5 divided by 0.1. 4.5 divided by 0.1 and length 0.6 meters. It's given here. So times 0.6 times, what is the magnetic field? Yeah, here. So into 1.8 into 10 raised to minus 3. And what will be theta? Theta is the angle between this current carrying wire's length and the magnetic field. Current carrying wire is in this direction and magnetic field is into the plane. So what is the angle between them? 90 degree. So what is sine 90? 1. So we need not consider this, and you can get the value of force due to the magnetic field. So you can use your calculator and find those values. So they got the value as 0.049 Newton. in both places, 0.049 Newton, 0.049 Newton. See, the magnitude of both forces are same. Therefore, this wire will remain in equilibrium because they are equal in magnitude but opposite in direction. So, the net force on this wire will be 0. So, you saw the next question. There are two figures given, figure 1 and figure 2. There is a current carrying wire AB which is 2 meter long, carrying a current 5 ampere in that direction, and they have marked a point C at a distance 0.5 meter from it. Now in figure 2, you have two wires AB and CD carrying current 5 amperes each. The current is in opposite directions and they are separated by a distance 0.5 meter, and they have marked 2 points X and Y on these two wires. And the wires are of length 2 meter. Let us see the question. Find the magnitude of magnetic field at C in figure 1. So here we have to find the magnitude of magnetic field. So at C is at a distance from a straight wire carrying current. So we have learned the formula for magnetic field at a distance from a straight wire carrying current. What is that? A. Magnetic field B is equal to mu naught I by 2 pi A, where mu naught is the permeability of free space and A is the distance from the wire. So if we substitute the values, you will get this as equal to 4 pi into 10 raised to minus 7, which is the value of mu naught, times current, which is 5 ampere, divided by 2 pi times A is this distance, which is 0.5. So when you put all the values, you will find the magnitude of magnetic field and you will get it in Tesla because this is in meters. Now let us see question number B. Okay, before that, let me just check the calculated value of magnetic field. It is 2 into 10 raised to minus 6 Tesla. Okay, now B, compare the direction of forces acting at point X and Y in figure 2. So this is figure 2. We have to compare the direction of forces. So we have to use the right hand rule and Fleming's left hand rule in order to find the required directions. Even though in the question they have asked just the direction of forces, it will be enough if you use these two laws and find the direction and mention that in words. Sometimes they may ask you to find the magnitude as well. So here we will find the direction and also magnitude. So let us first take this wire AB. It's a current carrying wire. So at this point Y, there will be a magnetic field produced by the current carrying wire. How can we find the direction of the magnetic field? By right hand thumb rule. So take your right hand, point the thumb in the direction of the current, curl your fingers. So you can see that up the current is coming out of this plane and down it is going into the whiteboard. So at Y, the magnetic field produced due to the current carrying conductor AB will be into the plane of this whiteboard, or if you are drawing in the paper, it will be into the plane of the paper. So let me represent it by this symbol into the plane and magnetic field due to A. Okay, this is the magnetic field experience. Now at Y, there is a current carrying wire CD now placed in the magnetic field B produced by the wire AB. So to find the force acting upon the current carrying wire placed in a magnetic field, you have to use the Fleming's left hand rule. So take your left hand, hold the first finger in the direction of the field, second finger in the direction of current, the thumb will show you the direction of force. So let us take the Fleming's left hand rule. Take your left hand, keep these three fingers perpendicular to each other. Let me point my first finger into the board and the current is in this direction, not that direction. So I'll have to rotate this, okay, my hand. So here the first finger, oh, it's very hard. Okay. So let me hold this into the plane of the paper, then plane of this whiteboard, and the second finger in the direction of current. My thumb is pointing downwards. So at Y, the force is pointing downwards. So there is no space here. I wrote it here. Let me move this 2 meters to this position. So force F is equal in downward direction because the thumb was pointing downwards. So at point Y, the force is downwards. So when you get a similar question for exams, you have to write here by right hand thumb rule. We can say the magnetic field at Y due to current AB is into the plane of the paper, and show this one sentence. Then you have to write by Fleming's left hand rule. You have to write the rule that the if first finger is pointed in the direction of the magnetic field, second finger in the direction of current, thumb will give the direction of force. Accordingly, we get the force acting on CD as downwards, or the force acting at point Y is downwards. So I am just writing the result here. But for exams, you have to mention these two rules as well. So here, force at Y is downwards. Okay. Now let us find what is the force at X. So we will use the same idea. Current is flowing in CD, so I have to take my right hand, point my thumb in the direction of current. See, my fingers are curling like this. So up at CB, at AB or at X, it's going into the whiteboard or into the paper if you are drawing this in a paper. So into it, so let me express it as the magnetic field B at this point due to CD is into the plane. Now again, in order to find the direction of force on this wire at point X, I have to use my Fleming's left hand rule. So take the left hand, hold your first finger, second finger and thumb perpendicular to each other. Hold the first finger into the paper. Current is in this direction. So I don't have to twist my hand. So here I have first finger into the paper board, second finger in the direction of current. Oh, how is thumb directed now? Upwards. So the force will be upwards at the point X. So here force F is upwards. So you will, for exam, you have to mention all the Fleming's left hand rule and the right hand thumb rule. I'm just writing here the result. What is the result? Force at X is upwards. See, they are in opposite directions. So these two wires will repel each other. We already learned that if the current are in opposite direction, they will repel each other, right? So this is the result. And if you want to find the magnitude of force, F, you know the force per unit length is equal to mu naught I1 I2 by, what is the expression for force? Force is equal to mu naught I1 I2 by 2 pi r. So you can use this. I1 and I2 are same. The distance r between them is 0.5. So you can get it as equal to 4 pi into 10 raised to minus 7 times I1 is 5 times 5 divided by 2 pi into r is 0.5. Now this is the force per unit length. So the total force you can find into length. So only if they ask that question. This question they have just asked the direction of force. So that's enough. Okay, let us see the next question. In the figure, so here a figure is given. The distance between two parallel current carrying conductors of equal lengths 10 meter is 5 centimeter. The point P is at midpoint between the two wires. So P is at a distance. How much will be this distance? 0. So it's 5 centimeter. So this distance will be 2.5 centimeter. Okay. What is magnitude of force per unit length of the wire A? So let us first solve A part. We have already learned the formula for force per unit length of two wires get parallel to each other and carrying current. So let me express that as F is equal to mu naught I1 I2 by 2 pi r, where r is the distance separating them. So all these values are directly given. This is equal to, we know the value of mu naught, which is a constant. Its value is 4 pi into 10 raised to minus 7 times I1. The current here is 12 ampere. I2, this current is 15 ampere, divided by 2 pi times r. R is the distance separating these two, that is 5 centimeter. 5 centimeter means 0.05 meter. We have to divide it by 100. So 0.05 meter. So 0.05. So you can use calculator, of course. So you do the calculation and you will get the value as 7.2 into 10 raised to minus 4. 7.2 into 10 raised to minus 4. What will be the unit? Will it be Newton? It's force per unit length. So the unit will be Newton per meter. So this is A part. Now let us see the B part of the question. If the direction of current through the wire B is reversed. So let me redraw it with the reverse case. Then will the magnetic field at P change? Analyze mathematically. So we have to check whether when we reverse the current, the magnetic field at this point P will change. So this should be case 1. And we have to find what will be the resultant magnetic field at the point P. Then we will redraw this figure with the current through B in the opposite direction as case 2. And we will again determine what is the magnetic field at point P. And then we have to see what is the change in the magnetic field at point P. So let me rub this part, otherwise I will not have enough space to solve. So B. So first case 1. Case 1, I am taking this figure without changing the direction of current in the wire B. I will be finding the magnetic field at P. Now magnetic field is a vector. So to find the total magnetic field at point P due to the wire A and B, we have to find the direction of magnetic field due to wire A and the direction of magnetic field due to wire B. If they are in the same direction, we will add their values to get the total magnetic field. And if they are in opposite direction, we will have to subtract them to find the net magnetic field at P. So first